Hey, so this is Joseph, and this is the sixth and final part of the second chapter of Stewart's Calculus. And we're going to be talking about linear approximation. And so, a linear approximation is basically a way of approximating a function at a certain value of x that you wouldn't just be able to solve or know. So, for example, this is a method for approximating the value of things like, the square root of 4.05, I don't know that, or for approximating sine of 0.81 or something like this. These functions that we don't just know off the top of our head without a calculator, and we can get a pretty good approximation for them without a calculator using this method. Alright, so here is what a linear approximation does and how we use it. So you use the tangent line at a and f of a, so the tangent line at that point, to approximate a function y, or a value y equals f of b, so f being that same function, where b is close to a. So I put that close in quotes because the closer b is to a, the better the approximation will be, and the farther away b is from a, the kind of not as great the approximation will be. And I'll show you graphically kind of how that works and why that makes sense. So the formula for the line used in the linear approximation is this one. And so we can see this line L is just in the standard form of a line. We've got f of a, and that's the y-intercept, plus f prime of a, so the derivative of a, and so that's the slope of the tangent line, x minus a, and so that the derivative times a, that also factors in to the y-intercept to give us that tangent line. So really this is just the tangent line at a. And so let's use this method, and you'll see how the linear approximation works to approximate. So if we have the function f of x equals root x, and so this is one function where we won't know all the values of that function. We don't know, for example, 4.05. We will use a linear approximation method to calculate 4.05. So we're going to try to ultimately figure out what this is, or find a very good approximation for it. First, let's get the tangent line for the graph. And now you might be asking, well, what do we use for a? Well, remember, a and b, in this case b is going to be 4.05, since we're trying to find the square root of 4.05, and let me just write out that f of x is the square root of x. This is the function we're using. So since we want b next to a, we have to think of two things when we're determining what our a value is going to be. We need to think of that it needs to be close to b, as close as we can possibly get, and we also need to be able to compute what that is in the function. So we need to figure out a value of a for which we know the square root, and that's close to 4.05. Well, 4, I think, is the best value. It's only 0.5 away from 4.05, and we know that the square root of 4 is 2, so we will have our a value be 4. So now let me write out that function of that. Alright, so here's that general function of the line again, and we're going to make it specific to the function f of x equals root x. We've got L of x equals f of 4, root 4 is 2, plus, now the derivative of f is 1/2, at a, we're trying to find it at a, is 1/2 4 to the negative 1/2 x minus 4, and then let's just simplify this out. 2 plus, that's going to be that's going to be 1/4 x minus 4. And so this is our tangent line. Oh. Right here. Alright, so here we have the curve. This is the square root of x. Y equals the square root of x. And we've got our value, we've got 4 right here. So let's look at the tangent line that we just found, and let's see it on this graph. So there's the tangent line, and we can see that it is tangent at x equals 4. Now let's see where 4.5 would be. 4.5 would be super close. It'd be right there. And look at that line is basically just about going through that point. The y value, the y value where that line goes through when so you can see L of 4.05 is going to be super duper close. It's just going to be just about equal to f of 4.05 because look at how close that is. And so this is one thing about this curve in particular, since it kind of straightens out as x gets bigger. Linear approximations are super great. To be honest, the linear approximation for 4.5 on this curve using the same line would probably be pretty darn good as well, but 4.05, since it's closer to 4, makes it even better. Now, if we were to make our b value super far away from 4, like if we were to make it 1, you see the value of the line at 1, or the y value of the line at 1 versus the y value of the curve at 1, this little margin of error, that's pretty big. That's a pretty big margin of error. Right here, that's too small of a margin of error for me to even draw in. So that's why for some curves this linear approximation works really well. And for any curve, if you get the change in a and b small enough, it'll work really well also. So now that we've looked at the graph, we can actually solve and do the linear approximation. And so we're going to try to find the value of L when x is 4.05, make that a big parentheses, and hope, and as we've seen on the graph, know that it's pretty darn close to the value of f of 4.05. And so we can solve for it here, the approximation here. So that would be 4.05 minus 4, which will be 2 plus a quarter of 0.05. And so this value right here is going to be very, very close to f of 4.05. So that's how linear approximations work. They're not too complicated, but they're very effective, and that's one of the best things that we can have in math and the sciences. Is a very close approximation, and even your calculators do a whole bunch of these, and they do a little bit more of a involved form of it called a Taylor series, which those are super cool, and we will talk about them in a couple chapters, but definitely get stoked for those.